All right, so good day. We're getting to some of my favorite parts of calculus about how everything connects together, about how derivatives of functions connect to the functions, the graphs of the functions, the geometry behind everything, how everything is all linked together. This is the cool part of like how geometry, algebra all come into play. It's all connected by calculus. I think before Isaac Newton, before Gottfried of Leibniz, before like Descartes, only like 400, 500 years ago, we had no idea how any of this stuff like worked together. So I think it's kind of fun and kind of cool how all of this pieces together. So the goal for today is all about how the derivatives affect the shape of the graph. Now we know from algebra that the zeros of a function give us your x-intercepts. So if the function equals 0, that's where our graph crosses the y-axis. Now what about the derivative? What about the second derivative? And so on. So here we got this in two different parts. Part 1, what does the first derivative say about the function f? What does it say about the graph? Now things that we know from past experience, the derivative, f prime of x, it gives us the slope of the tangent line at any point on the graph of x. Okay, that's what we've been talking about. We've written equations of lines or equations of tangent lines. Now thinking back to past experience, algebra 1 even, when the slope of a graph is positive, think back to a line, it's moving up and to the right. When the slope of a graph is negative, it's moving down and to the right. So positive slope, it goes up, negative slope, it goes down. Well, the derivative tells us all those little bits every step along the way. Now that gives us this idea of when a function is increasing, when a function is decreasing. In previous classes, you used the calculator to find maximums, minimums, and you inferred that in between these points, the graph was increasing, going up. When was the graph going down? Well, that's what the derivative tells us. So we have our increasing, decreasing test, sometimes referred to as the ID test, or just increasing, decreasing. If the derivative is positive on some interval, then the function is increasing on that interval, the entire thing. It goes both ways. If our function is increasing, then the derivative is positive there. We use that when we sketched graphs earlier on. If the derivative is negative on an interval, then the function is decreasing on that interval. Oh, it makes sense. So if a function is going down, the first derivative is going to be negative. Or if the first derivative, the slope, is negative, the function is going to be decreasing. And so just by looking at the signs, positive or negative, of the first derivative, we can tell whether a graph is going up, it's increasing, or a graph is going down, it's decreasing. Let's see that in play. So here we've got a function, f of x is 3x to the fourth minus 4x cubed minus 12x squared plus 5. Where is this function increasing? Where is it decreasing? So I want to identify intervals of increasing, identify intervals of decreasing. I'm going to take the first derivative of this. So finding the first derivative, that's going to give us power rule all the way. That's 12x cubed minus 12x squared minus 12, nope, that's a lie, minus 24x. All right, now that's a polynomial. I'm going to factor that. I notice there's 12, 12, and 24 is a multiple of 12, and everything's got a factor of x. I'm going to factor 12x as my greatest common factor between everything. That would leave us with x squared, subtract x, subtract 2. And I think I could factor that one more step. So that's f prime of x. It's 12x. It is x subtract 2, x add 1. All right. Now, thinking back, what do I know about polynomials? Our first derivative, this is a cubic polynomial, and I know cubic polynomials, something like that. I can see that my derivative, excuse me, our derivative is 0 at x equals 0, x equals, excuse me, negative 1, x equals 2. So my first derivative is going to look something like that. Y equals f prime of x. So here, all the way to the left, our derivative is negative. Our derivative is positive on that section. Our derivative is again negative on that section. Our derivative is again positive on that final section. So, and I know taking a step back, I know our derivative graph is going to look like that because this is a positive cubic polynomial. And I know those designated zeros by setting the derivative equal to 0. I'm going to use that, and looking at the function, I can see that our graph, f prime of x, is less than 0. Our derivative is less than 0, meaning f is decreasing. Negative infinity to negative 1. It is decreasing from 0 to positive 2. And that is looking at those two sections. f prime of x is positive, meaning f is increasing, on those sections where our derivative is positive. So we're increasing from -1 to 0, and again from 2 towards positive infinity. Now I can also look at this, and another way, rather than requiring me to think about, okay, what does that graph look like? Instead, let's forget about that. I'm going to use what's called a sign chart. And you may have used this back with rational functions, trying to figure out what does the graph of a rational function look like. I'm going to take a number line, and I'm going to partition my number line using those zeros that I found from our first derivative. So to partition, I'm going to break this apart. We have 3 spots where our first derivative is equal to 0, at -1, 0, and 2. Now what I'm going to do is I'm going to ask myself, is this positive or negative on each individual section? And so I'm going to pick some number, I don't care what the number is, on that interval. So I'm going to pick some number to the left of -1, say -2. I don't care what the value is, but I'm going to take that -2 and I'm going to substitute it in to each of our factors. Now if we plug in -2 to 12x, we're going to get something negative. If we plug in -2 to x minus 2, that's going to be -2 subtract 2. Negative subtract 2 subtract 2 is negative. If we plug in -2 plus 1, we're going to have -2 plus 1. That's going to get us negative. We have 1, 2, 3 negatives. 3 negatives, the whole thing is going to be negative. I'm going to pick some number in between -1 and 0, say -1/2. If I plug in -1/2 to 12x, I'm going to get a negative. If I plug in -1/2 to x minus 2, we're going to get negative. If I plug in -1/2 to x plus 1, we're going to get a positive. 1, 2 negatives, 2 negatives is positive. The whole thing is going to be positive on that interval. Next, I'm going to pick something in between 0 and 2. Okay, say 1. If I plug in 1 to my first factor, 12 times 1 is positive. Plugging in 1 to the second factor, 1 minus 2 is negative. If we plug in 1 to x plus 1, 1 plus 1 is positive. I don't care what the value is. I care we have 1 negative. 1 negative, the whole thing is negative. I'm going to do the last thing. I'm going to pick some number greater than 2. 15, just because that's the number I picked. If we plug in 12 times 15, positive. 15 minus 2, positive. 15 plus 1, positive. The whole thing is positive. So those give us our intervals where we're going to be positive, increasing, or negative, decreasing. Notice that interval left of -1, it's negative or decreasing. Between 0 and 2, negative, decreasing. Between -1 and 0, positive, increasing. Greater than 2, positive, increasing. That's our increasing, decreasing, using a sign chart or referencing a function graph. Now, previously we talked about local maximums, local minimums. Local maximum or local minimum occurs at a critical value c. That critical number, those for which the derivative, the first derivative, is either 0 or undefined. So if we have a local maximum or minimum at some point, then that point must be a critical number. But also, not every critical number actually yields a maximum or minimum. So max-min implies critical number, but critical number does not imply max-min. Well, what we just did tells us, actually, if we have a maximum or minimum. You actually lose my face here, because I'm actually excited for this. So maybe you can tell in my voice. All right, suppose we have some critical value, either where the first derivative is 0 or undefined. Looking at, going back to that sign chart, if the first derivative changes from positive to negative at some point c, I'm looking down at that first, if we change from positive to negative, we're going to have a local maximum. We had to pass through 0. If our first derivative changes from negative to positive, we're going to have a local minimum. If, however, here's where our critical point fails to have a maximum or minimum, if we go from positive to positive, passing through a critical point, or negative to negative, passing through a critical point, we do not have either a maximum nor a minimum. So let's actually put this in context. Think about this same function. F of x equals 3x to the fourth minus 4x cubed minus 12x squared plus 5. Actually have all the work done back over here. All right, so we have already found our first derivative. I set the first derivative equal to 0. Those are our critical values. Those are the critical values for f. Now, we've already identified where's our function increasing or decreasing, and I second use this sign chart. Well, look at these values here. Our function is changing from decreasing to increasing. Now, think about that. That means our graph is going down, and all of a sudden, it had paused, and then it started going up. That tells us that x equals -1 is going to be a local minimum, at least a local minimum. If we look at the second critical point, x equals 0, our graph goes from increasing to decreasing. So the graph is going up and then going down. That means we have to pass through a local maximum. And lastly, our third critical point there, +2, our function is decreasing to increasing. That means our graph is going down and then it's going up. So at that critical point, we pass through another local minimum. We call this the first derivative test. And the first derivative test identifies whether or not we have maximums or minimums at critical points on a function. So we look, does our graph change from positive to negative? Positive to negative, we have a local maximum. If our graph changes from decreasing to increasing, the first derivative changes from negative to positive, we're going to have a local minimum. Let's try that with one more function here. Find the local maximum and minimum values for this function g of x equals x plus 2 sine x on the interval 0 pi over 2. 2 pi. First thing I'm going to do is I'm going to take my derivative. Take the derivative, find the first derivative. So g of x is that, and g prime is going to be 1 plus 2 cos x. Again, we are looking on 0 to 2 pi. Now I want critical values. So critical numbers, I'm going to set the first derivative equal to 0. So 0 equals 1 plus 2 cos x. I'm going to solve this. So I'm going to subtract 1, divide by 2. We've got cos x equals -1/2. And because I am a good, proper student of calculus, I remember my unit circle. Cosine is negative quadrants 2 and 3. And so our angles on that interval 0 to 2 pi are going to be 2 pi over 3 and 4 pi over 3. Those are our critical values. Now I'm going to set up my sine chart. Now we are going from 0 to 2 pi. I'm going to partition my number line, my sine chart, using those critical values. I'm going to break it 2 pi over 3, 4 pi over 3. Now I am going to be referencing back to g prime of x being 1 plus 2 cos x. Now here, I can't exactly say, I don't have factors that are being multiplied. What I'm going to do is I'm going to evaluate kind of what's positive, what's negative. I'm going to pick some angle that I know between 0 and 2 pi over 3, some angle that I can easily evaluate on 1 plus 2 cos x. In between that, pi over 2 is a good example. G prime of pi over 2 is going to be 1 plus 2 cosine pi over 2. And I know that is 0. So 1 plus 0, that's a positive value. So our function is increasing from 0 to 2 pi over 3. I'm going to pick something in between 2 pi over 3 and 4 pi over 3. Maybe, pi. So, okay, g prime of pi. That's going to be 1 plus 2 cosine pi. Cosine pi is -1, so we've got 1 plus 2 times -1 is 1, subtract 2 is -1. Oh, it's negative. So our function is decreasing from 2 pi over 3 to 4 pi over 3. You probably guess what happens next. I'm going to pick some number on the next interval. So something in between 4 pi over 3 and 2 pi, maybe 3 pi over 2. So our derivative at 3 pi over 2 is 1 plus 2 cos 3 pi over 2. And cos 3 pi over 2, ooh, that's 0. So 1 plus 0, that's positive. So our function is going, whatever it's going to look like, it's increasing, then it's going to be decreasing, then it's going to be increasing. We have two minimums, two maximums. All right, now immediately what I see is that our function went from increasing to decreasing at 2 pi over 3. So x equals 2 pi over 3 is going to be a local maximum. Our function went from decreasing to increasing at 4 pi over 3. So x equals 4 pi over 3 is going to be a local minimum. I mentioned two mins, two maxes. We're going to think back to our extreme value theorem from the other day. The extreme value theorem says that on a closed interval, we're guaranteed to have an absolute maximum and an absolute minimum somewhere on that interval. Now we find the critical values, we test the critical values, we also need to test the endpoints. Now what I see here is at x equals 0, get rid of that, x equals 0, thinking about the graph, from that endpoint it's going to be increasing. That endpoint is going to be a local, or at least a local minimum. Have to test the endpoints, check the endpoints. On the right side, we're increasing and then stopping at 2 pi. That means that 2 pi has to be at least a local maximum. If I wanted to find whether or not these were absolute maximums or minimums, I would need to go in and evaluate the function. We can test f of, rather not f of, but g of 2 pi over 3. Plugging that in, we're going to have 2 pi over 3 plus 2 sine 2 pi over 3. We'll test g of 4 pi over 3. So that's going to be 4 pi over 3 plus 2 sine 4 pi over 3. We're going to take g of 0, and we're going to take g of 2 pi. You can go on and check the rest of those. That's what we've got for part 1. See you on the flip side for part 2.